people could submitting questions in the chat. I'm going to wait 2 more minutes for everybody to show up. And then we'll get the show on the road. So. Sophia, there should be, for readings at least, there should be distinct readings for last week and this week. So we're not moving on to block 3 yet. You can if you'd like, but I want to talk a little bit about things like bias and heteroskedasticity because the assignment asks about problems with the linear model, and it occurred to me that you may have forgotten about things like bias and heteroskedasticity when analyzing models. So I just wanted to talk a little bit about that today from a perspective that's sort of more theoretically informed than you got before in spatial modeling. No, we're not. My encouragement would be to make sure that you understand the discussion of linear regression problems, or I guess things that affect the quality of a linear regression from the reading last week. We'll be revisiting some of that stuff today. So yeah, you can't move on if you think that you've got it all. I just wanted to revisit some of those issues with collinearity and heteroskedasticity and things like that. "30 more seconds. If you have a question, please pop it in. Okay, time to go. So the first thing we'll do in this session is to talk a little about questions from the assignment. Thanks everybody for showing up today. I know that there's a lot going on, so I also wanted to check in a little bit about how the course is going to go in the future. I have a little bit of extra feedback or things that I've learned from the assignments that I've just finished marking everybody's first assignment. And then I want to give you a short discussion of problems with linear regression that you all have heard before, hopefully. I wanted to do this in a bit more of a kind of theoretically informed perspective so that you can use it in your assignment when you have the question of sort of the can you detect any problems with this linear regression. So the first part that I want to cover today is the questions in the assignment. Most of you have now put questions in the chat that I'll address specifically. So Edward asks, with individual mean for each year in section 2, are they their own category, serving their own intercept, or should we fit an intercept with model? Not particular about what you do. So both of those model expressions have a distinct mean in each year because it's a categorical variable in that mode. So I don't want you to fit an effect where you just have one effect for all years. That is, I don't want you to treat year as a numerical variable. So as long as you're treating year as a categorical variable, I don't mind which specification you pick, either the fixed effect or the contrast mode. If you pick the fixed effect mode, I want you to explain why the statistical, like the significance of the different means that you estimate. I want you to explain why you see what you see. And if you pick the contrast encoding of those values, I want you to explain also you see what you see. So I think some of you are overthinking this. I'm not going to mark you incorrectly for doing one or the other, as long as you do something where there's unique mean in every year, and give the correct explanation for why that encoding of the model has the significant effects that it does. Okay, so that's all I'm really talking about there. Neve asks, I'm having problems with getting a unique mean for each year instead of for the minimum year in the regression for 2. I'm not sure how to help with that. All that should be required is having the year as a factor. So you may need to say that your year, convert the year to a factor variable. Emily asks, what do you mean by unique mean and why is it useful? Well, I don't want you to estimate the model, which is 1 plus beta times year. There's only 1 year effect that measures the effect of increasing 1 year on the data. I want you to estimate the model that has 1 plus alpha 1996 plus alpha 1997 plus, or I want you to estimate the model that has alpha 1986 plus alpha 1997 plus, so that's either the contrast or the fixed effect. I don't mind which one you pick. I do not want this one, which treats the year as a numeric variable. Does that make sense? When I say unique mean, I'm saying either a contrast or a fixed effect. I don't care which one you fit as long as you do that. That should be clear to everybody now. I got a lot of questions about that in the lab. I know that it's kind of confusing, but my goal is to try and get you to think about these things by their kind of impact rather than by telling you these kind of like abstract theoretical points like fit a fixed effect. What's more important is for you to get this model on the bottom here is treating every year as a distinct group, whereas this model up here is treating the year as a continuous variable. So just make sure that you're doing that and you're fine. And then to re-answer Sophia's question, we're here for the readings. Are we now going into block 3? No. I'm going to be talking a little bit about the issues with linear regression that we see from the Introduction to Statistical Learning chapters chunk, as well as some of the stuff from the Gelman on working with linear regression. So it's just going to be problems that can affect your linear regression. Second thing that we've kind of talked about, or the second thing I have on my agenda today, talk a little bit about talk about a little bit about feedback from grading. And I have 2 points that I'd like to cover in the feedback from marking. One of them is when to quote in R. And the second one is plagiarism. Okay, starting with when to quote in R. So when we're dealing with variables in the tidyverse, some of you wrote code that looked like pivot longer, and you put column A, colon, column B, and you put names 2, let's say, let's call that names 2 is equal to months. Just taking this simple example. If you look, quotation marks occur here. There are no quotation marks here. So why? Why these things? Well, these are existing columns in a data frame. Because they're existing columns in a data frame, and generally speaking, this is going to be coming off of a pipe, the data frame is to our left, we know that these two columns are a part of the active data frame, or the data frame that we're piping to the right. We don't need to quote those names. Okay, if they're columns in the existing data frame, we generally don't need to quote those names. If we're creating new names, we need to quote those. So if I'm calling some new set of names, some new set of column names, or splitting columns into new column names, all of those things need to be quoted. Now, if you see an equal sign like this, it's nearly always the case that quotations are going to be on this side of the equal sign. It is extremely rare that quotations will be needed here. Extremely rare. The only time where that's going to be something you need is in something like summarize. If I want to call something column with spaces is equal to something. So if I'm using a column name with spaces or special characters or anything that is not standard, I'm going to need the quotations on the left side of an equal sign. Otherwise, it is almost never needed. Ever, ever, ever. So you should never need to quote arguments that you send to functions. The only time you need to quote is when you're creating new names or you're referring to a string. Okay? The tidyverse has this concept called quasi-quotation. I'll get to your question, Georgia. Quasi-quotation. If you see that word, quasi-quotation, in the help text, that refers to you not having to use quotes. It means that anytime you don't quote something like a column name, it's going to automatically inspect the data frame for that reference. So it's going to look for column A and grab all the columns between that and column B. And you don't need to use anything that refers otherwise to those columns. Okay, so Georgia asks, does it matter if you use underscores? Or, sorry, does it matter if you use double or single quotes? No, not in R. So you should be able to use single or double quotes. In R, the backtick, which is a special symbol, is different from the quotation mark below. So the backtick is a special type, but you can use single quotes or double quotes, and it's both fine. Both of them are fine. In some programming languages, they are different. So you will be grateful to your future self if you use double quotes all the time. So there's no difference in R, but newer programming languages for data analysis are increasingly enforcing a difference between single and double quotes. Most of you also kind of so with this kind of quasi-quotation stuff, just make sure that your quotes are always kind of on the right of the equal sign, and that anytime you're referring to a column name, that does not necessarily have to be quoted. Okay? Cool. So I saw a lot of, very wild things, some of which I didn't even know was proper R. Whoops. So one thing that I learned from someone's assignment is that if I'm assigning to a variable in R, and I'm saying like do something, so I'm running some long function or I'm doing something fun, I can actually put quotation marks around my result. And that gets updated to a proper name. I had no idea that was valid R. And I've been programming R since I was 23, 22 maybe, almost 7 years. Long time. I had no idea that this was valid. So that is definitely not the right pattern. Quotation marks should always be on the right side of an equal sign. Never use them in an assignment like that. It's just not, it's not the way that they're intended to be used. Now, R does a lot of magic and is really forgiving in what it does. But you should never need to do that. You should never need to put quotation marks on the left side of an assignment like that. Okay? Cool. So that's when to quote in R. When you're using something that comes within a data frame, especially when you're using tidy tools, you usually do not need to quote the column names. If it's a new name, you need to quote. The thing I wanted to talk about in today's meeting is plagiarism. A couple of your assignments had really similar errors in the same fashion. So, out of all the scripts, there are some errors that people make in common. But when you make a really funny error, and you make that error with your friend, I can pick it out. If this happens in the next submission, where there's a substantial amount of code that's written similarly between two assignments, and I can identify that the code is pretty much the same across an entire submission, you're going to have a bad time. I am generally not interested in penalizing students for working together. And I know it's hard to figure out the bounds between an appropriate collaboration and an inappropriate collaboration, especially when the outcome is your code. But this becomes challenging when the only thing that I really have to assess you on is what you write in your language and in your code. So, in some of your assessments, there will be a sentence like, this is substantially similar to another paper that has been submitted, or this is a very interesting error, and I've seen it happen in a couple of other places in other scripts. Please don't do this again. If I have specifically given a warning like that, please try harder to keep your code independent from the people you're working with. Because it seems like in those cases, it has crossed the threshold. And I don't want to be that guy to raise these cases, so nothing's going to happen in this first submission. However, I would encourage you seriously to try and work a little bit more independently. I'm more than happy to work with you through sort of specific code issues in office hours, in breakout rooms. Tom and Lenka are also around, but it's really challenging to mark what you understand when you're copying code from, a large chunk of TMAP code from a book, or, sharing the very same kind of weird way of changing column names. So just be a little bit more careful about that. It's always better to do something simpler if it means that you write it. So I don't really care if you can make a highfalutin shiny app if all you're doing is copying some bit of code that you've copied from Stack Overflow and are changing the input data. I care much more about the people that are able to do this based on the thing that they learn about in the program. I really, really don't want to see cookbook style programming. Now, the good thing is that from here on out, there's not going to be a lot of programming. There's mainly just going to be fitting a model, thinking about a model. But I just wanted to raise this because this kind of surprised me. I have a lot of trust for you guys to do things this way, and I've structured the course in a way that kind of rewards individual engagement in this manner. So yeah, I would hate to not be able to do that because this is a problem in the future. So if it remains a problem in the next submission, then we're going to have to treat these cases in a much more serious fashion. So I just wanted to mention that before we move on. All of you are aware of the regulations regarding plagiarism, and I just want, but I think that it'll be okay and we can move on. So that done. The very last bit I want to talk about before we move to the content is the plan for the course. Shoot. Oops. Plan course. So I've had kind of 3 different suggestions that I've heard from people about stuff that they want to learn for the final chunk. Kate, I'll get to that in a second. The first thing that I've heard some stuff about is the planned unsupervised learning. The second one is visualization. The third one was generalized additive models. And the last one that I've heard was someone asking about time series. So this week, after the assignment is due on Friday, I will start a poll where you'll be able to use some kind of voting method, either ranked preference or bullet voting or something, I don't know. And you'll be able to indicate whether or not you find one or more of these to be interesting for the last chunk. I'll have a little sort of paragraph about what they are so that you won't be voting in the blind. That'll be open for 1 week. And then whatever you vote on will be running for the last chunk. Okay? But right now, I have 4 suggestions. If you want anything different, you need to let me know loudly. Okay? Cool. Kate has asked, when will we get the marks back for the assignment? Well, the marks are due back to the office on the 5th of November. So I assume you'll probably get it fairly soon after that. I don't think you'll get it in time for this submission. And that's okay. I understand that. It's cool. Don't worry about it. I'm marking these things with that in mind. But for those of you who, are kind of concerned about your feedback, just go with the general feedback that I've given you in class. And then again, try a little bit harder if you're concerned about sort of code overlap, try a little bit harder to work independently in the last couple of days here. But again, I'm marking these things with the knowledge that you won't have specific feedback in time for the very next assignment, which is why we're doing these kinds of answer sessions on Fridays. So, sound good? Cool. Okay. That said, is there any more questions before we move on to bias and heteroskedasticity and multicollinearity? Cool. Okay. Seeing none, we'll move there. So this next part of the course, or next part of this chunk, is trying to give you a bit of a critical sense about what regression models are doing when you fit these slopes or these odds ratios or these various kinds of things. So I've called this lecture Problems with, that's not how you spell with, Problems with Linear Regressions. And there's a couple of main points that I think are the most important points. I want to talk a little bit about bias. I want to talk a little bit about heteroskedasticity. And I want to talk a little bit about multicollinearity. Because these are three things that regressions tend to have problems with. Now, to summarize each of these really simply, the problems that regressions have with bias is that even though they are unbiased on average, they can be biased for special groups. So that's the main problem with bias in regression, is that on average, your predictions will be unbiased. They'll be on the money. But sometimes we care about the prediction accuracy of special groups, and that becomes important. Regressions don't know anything about the structure of the data beyond what you tell them. And so it becomes important for you to understand why that matters. Heteroskedasticity affects regression coefficients in a very special way. And I've seen a lot of dissertations and a lot of past spatial modeling at 2 assessments that can correctly identify when heteroskedasticity exists, but not necessarily why it matters. So for a working definition of heteroskedasticity, I'd like you to think of it this way. Heteroskedasticity means that even though the model assumes uncertainty is consistent, it is not. So heteroskedasticity, in plain language, is the fact that your model assumes that uncertainty is consistent, but it is in fact not consistent. Finally, issues of multicollinearity are another one that students generally understand and are able to reproduce a textbook definition of, but they don't really demonstrate kind of why it matters and why it's important. So I want to try and give you a short sense of that today so that you can use that intuition later. So multicollinearity is, in a plain language, even though the model assumes you can change x1 separately from x2, you can't. So one thing should be clear here. Bias is not about an assumption. Bias is just a property of some models and some groups inside your model. Heteroskedasticity is about an assumption of uncertainty. Sophie, heteroskedasticity is related to the residuals, and we'll get there. It's an assumption about our errors or our uncertainty in the model. Likewise, multicollinearity is about an assumption that you can change two variables separately. Georgia asks, what's x1 and x2? This keeps confusing me. They're just kind of variables that I'm using to stand in for other things. So in the Introduction to Statistical Learning book on the chapter with regression, that might have been radio advertising spending and newspaper advertising spending. When I say x1 and x2, normally I'm just referring to different variables in a model. So I could rewrite this by saying, even though the model assumes you can change variables separately. Oops. Would it help if I wrote that? Cool. X are the independent variables. They're the thing on the right of the equation. Remember, if our regression equation is y is equal to alpha plus x1 beta 1 plus x2 beta 2 plus e, these are our x variables. Yeah, no problem. I get that. I'm sure that your conceptual understanding is great. It's always just like one of these language things, so no problem. Happy to clarify. So multicollinearity is about an assumption. Heteroskedasticity is about an assumption. Bias is just an intrinsic property of your model. So I'd like to talk a little bit about bias here. So I'm going to skip down and we'll talk about bias. So every time you run a regression and you get a bunch of points and you fit a regression line, that regression line has a unique property. If I look at the average of every y minus my predicted y, so if I take their sum from I equals 1 to the number of points I have, if I add up all of my predictions, that is equal to 0, or prediction error. So when someone says that a linear regression is unbiased, what they mean is that on average, the prediction errors are 0. If I overpredict some, I will underpredict others. So when linear regression talks about bias, that's what it means. There's another notion of bias that's used when people talk about linear regression. Just so you know what that is, I'll show you that now. We tend to think about linear regression having two parameters. Alpha, which measures where the line crosses the or the y-intercept, and beta, which tells us the slope of the line. In higher dimensional spaces, when you have more x variables, you might have more beta. Linear regression also has the property where the expected value for our guess about beta is equal to the actual beta. So this is also a property of unbiasedness that people talk about with linear regression. So you can distinguish these things by recognizing the fact that our errors average out is about unbiasedness in prediction. The fact that our estimated slope is equal to the theoretical slope we can't know, that on average the expected value of what we estimate is right, that's estimation unbiasedness. And we'll talk about multi-level models which violate these two properties next chunk. But what I'd like to get you to think about is that even though both of these things are dealing with the average behavior of our predictions or our estimator, there can be really weird things that happen underneath the surface when we focus on special groups of observations. So yes, alpha is the intercept and beta is the gradient, how we normally write the regression. So just for now, I'm going to ignore the estimation bias and just talk about prediction bias. Looking at our point cloud in this example that I've drawn, all of these points in this region here that I've shaded in green, all of those are larger than their prediction. And all of these, which I've shaded in red, are smaller than their prediction. Emily asks, the fact that prediction errors are 0 on average makes a model unbiased or biased? It makes it unbiased. So bias is the property that you're sort of on average inconsistent. On average, you're not getting the right answer. So if your model has prediction errors that are 0 on average, that model is unbiased. All linear regressions are unbiased. Now you can do special things to them to make them biased, and they can also be biased for particular groups or particular ranges. But all linear regressions have the property that the average of their prediction errors is 0. That means that all linear regressions are, on average, unbiased. But they can be biased for groups of observations. So like I've shown here, this group of observations is all above its prediction. And this group of observations is all below its prediction. Now, this is generally speaking not something a linear regression is going to understand. This becomes important when I might be thinking of these things as groups of observations. What if all of these observations were, I don't know, let's say Brexit votes in the north of the country. This would reflect the fact that the average trend always underpredicts those votes. Likewise, if this were the south of the country, then this would mean that our model always overpredicts those ones. So when you think about your model and you look at its predictions, it may become important to split your outcomes into different groups and understand how your predictions for certain groups may be wrong. On average, it will be unbiased. But just because it's on average unbiased does not mean that it's unbiased for all observations, or for all kinds, or for all groups. So all I'm suggesting here is that when you investigate bias in your model, you think about things like this. One thing you might observe, say, if you were to fit a model based on our house prices data that we've been working on a little bit, right? I get a little bit of a trend where my house prices go up and then they go down and then they keep going up. So if I fit an effect and I look at residuals for these models, they'll be centered on 0 on average. But they might have a ghost of the pattern that we see in Y, or they might have something else. It could be that our model systematically mispredicts house prices in a certain range of years. On average, the residuals will be 0. But what if our model completely misses the financial crisis, or seems to have this strong temporal dependence? All I'm suggesting is that bias, when you think about it in terms of your linear regression, it'll be good on average, but it might miss special groups of observations. That's my main point. Okay? So you can identify that by analyzing the residuals, either by grouping them together for a group you think might be mispredicted, or by plotting it against one of your X variables or things like that. Okay? So that's bias. Heteroskedasticity happens when your model assumes there's a constant uncertainty, but there's not. The plot that you've seen many times that students normally use to diagnose heteroskedasticity is a plot of the residual versus fit. And you see oftentimes a kind of funnel shape. Which suggests that as our predictions get bigger, our prediction errors get bigger. This in general is right, that heteroskedasticity means that your variance isn't constant across your observations. But let's go back a little bit to the regression itself and think about what this means. If I have heteroskedasticity, then I might have a regression where my slope and intercept are like this. And if I were to draw a confidence interval, the linear regression is going to say, okay, all of the possible lines are going to go through that bound. And they're going to go on the other side of that alpha. So the uncertainty in your slope will manifest as a bunch of different possible lines that kind of fuzz around the original line. It represents what's sometimes called an envelope around your line. Okay, and you've done this before actually in Spatial Modeling 1 when you were asked to do a bunch of simulations about correlation coefficients. But my main point is that heteroskedasticity implies a situation where your uncertainty about your slope in one point might actually be different from your uncertainty at another point or at another point. So heteroskedasticity usually means that there's some difference in uncertainty about the variance of y in your pattern. And you might need different variances for different values of x to capture that. So the uncertainty is not constant over x. Now that's just one type of heteroskedasticity. You could also have heteroskedasticity that changes depending on groups of observations, just like bias. And the regression will assume that the uncertainty is constant over all groups. Practically speaking, Patrick asked, in this example, would this mean that all possible lines would have to go through 3 confidence intervals? Well, this is where we get to the point. In practice, this would mean that the right confidence interval is actually going to be long, or at least some kind of average between this one, and that one. So nobody cares about heteroskedasticity as heteroskedasticity. Everybody cares about heteroskedasticity because it increases the confidence intervals of your regression. If the true confidence interval for beta is this one, and your model does not account for heteroskedasticity, you're going to have too narrow a standard error, because you're not going to account for the fact that variance changes. So heteroskedasticity means that you might mistakenly conclude that there's a significant result when there's not. Your model is not accounting for the fact that uncertainty changes. And this is important because you might increase your rate of false positives. The way that we say that in econometrics is that if you don't correct for this, you'll have deflated standard errors. And that if you correct for heteroskedasticity, your uncertainty actually might increase. So this is why heteroskedasticity matters. It's not just that it exists, it's that it increases your uncertainty. It's that the assumption of constant uncertainty means that, generally speaking, you're going to understate the uncertainty. Okay? So that's heteroskedasticity. The very last thing is multicollinearity. Talked a little bit about this when we were talking about the fixed effect model and the contrast model, and I won't have too much time to go into it here. But what I'd like to kind of make you think about is that the typical linear regression works like this. If I have an x variable and a y variable, my assumption is that I can increase a unit x and see an increase in a unit y. If I have 3 dimensions and I have some linear regression that has some height there, and this might be x1, this might be x2, and this might be y, I'm actually going to get a whole surface of these regressions. Okay, I'm going to get a whole surface of these lines in multiple dimensions and higher dimensions than just your standard linear regression here. You're actually fitting a regression plane. Okay, but here I'm just representing it as a single line to simplify the drawing because I can't draw infinite planes. And the assumption is, again, that x1 is what's called orthogonal to x2, and that I can increase x2 without increasing x1. So I can move this way without moving that way. It's hard to see again in 2 dimensions. I have a 3-dimensional regression plane on my website, actually. Let me pull that up for you. So I'll put it in the chat if you want to see it. Now, multicollinearity, a great example of this, might happen when, let's say, you have 2 parties and you're trying to predict, I don't know, the inequality in a given county. Oh, I'm sorry, I'm getting hailed on here. I'm trying to predict the inequality in a given county. And if I make that a function of, let's say, my party 1, let's make this less abstract. Let's say I'm talking about that in terms of the percentage Democrats that vote there and the percentage Republicans that vote there. And I've got that in a model. Okay? Just focusing on my x1, x2, and plot here. So let's say that this is percentage Dem, this is percentage Republican, and this is inequality. Is it possible for me to increase my percentage Dem without increasing my percentage Republican? Is it possible to change this without changing that? The answer is no. Increases to percentage Dem will decrease percentage Republican. This is called collinearity. The two have a linear relationship. So when this happens, well, indeed, thinking about it as a zero-sum game. So when you move in one direction, if you can't isolate that move from other variables, then you have collinearity. And there's a certain amount of collinearity that's actually acceptable in multiple regression. But what you don't want, and what you see sometimes, is that two variables will add up to be one. So if I add the percentage Democrat plus percentage Republican, I'll get something that's extremely close to 1 everywhere, or extremely close to 0.6 or 0.7 everywhere. So when we're practically thinking about inequality, or when we're practically thinking about multicollinearity, the important thing is that you have these variables that are possible to be changed separately from one another. Your model isn't going to understand this. And in the worst case, if you have perfectly collinear inputs, your model will just dump out garbage and possibly a warning. But the issue with multicollinearity is that you can't change one of the variables without changing the other. Practically speaking, what does that mean for analysis? Well, you can still trust your predictions, and you can still, generally speaking, trust the general effect of changing both of the things at once. So if I have a model that has a bunch of collinear factors, then I can trust the fact that changing some of those altogether will have an effect. However, I can't assume that I can change percentage Democrat without changing percentage Republican. They're structurally related. There are other kinds of collinearity that can happen that aren't this strong, but will still affect your model. So the main point is that it jeopardizes these assumptions that I can change one thing without changing another. So those are the three problems that I wanted to talk about in terms of regression. Bias, that even though the regression is unbiased on average, it can be biased for special groups. Heteroskedasticity, which is that the model assumes that uncertainty is consistent when it's not. And multicollinearity, which assumes that you can change variables separately when you can't. In a case of a model that is biased for particular groups, the effect of that, which is the most important part, is that our predictions are going to be consistently off for things in that group. For heteroskedasticity, the effect of that, generally speaking, is that our uncertainty is understated. For multicollinearity, the effect of that is that you can't think about variables separately. Their confidence intervals and point estimates may be wrong, but the sum of their effects might be okay. So all I wanted to do today was to give you kind of the three big ideas about problems with linear regression that then motivate a bunch of other kinds of regression corrections and transformations and things like that. But the main point is not necessarily that you can identify them, but it's understanding why they matter. It's good that you can tell if they exist. It's better if you know why they're important. So that's all we really have time for today. But I wanted to get to this so that you were kind of armed with the theory of how to attack the question about can you detect anything wrong with your linear regression in the assignment. So that's all. I have to go because I have another meeting with the student in office hours, but if there are any further questions, I suggest that you either book some time with me or prepare them for the lab on Thursday. Sound good, folks? I'm sorry that I had to spend time dealing with kind of logistical stuff ahead of time, but it's important to make sure that we are clear on the ground rules for the next submission. So